Hi again, everyone. So this presentation, I'll be presenting about external sprinkler systems for bushfire protection. I'll be taking a pretty high-level view of several different research projects that we've done in recent years looking at bushfire sprinkler systems. And I guess just to set up the context initially, there are a lot of households already using bushfire sprinkler systems in Australia and overseas as well, but it seems to be predominantly an Australian idea. The sophistication of the different systems that are being used in the field varies widely. So from the field work we've done looking at different systems, they go everywhere from sort of garden sprinklers with garden hoses connected to them all the way through to professionally engineered, very sophisticated designs. Typically, they're promoted as being an additional layer of protection on top of the passive protection measures that are needed, and under the NCC, that is what they need to be for compliance. Because they're not currently recognised in the NCC or in 3959. But we do have our own bushfire sprinkler system standard, which is AS 5414. The perception amongst the public seems to be quite strongly from people who are trying to design these systems that they need more detailed evidence-based guidance. That comes through fairly strongly in our interactions with the community anyway. And sprinkler systems within our industry are quite a polarising topic. So there are quite a few strong opinions that either they'll save the world and why aren't we using more of them, or they're very unreliable and very dangerous and shouldn't be promoted. So in this presentation, we're not trying to take a view either way on that. We're just showing some of the research that we've done. And it is a fairly young research field. The science isn't all there. So there's a lot of room for more science to be gathered in the future. This data is taken from one small study we conducted. It was quite an in-depth study, but a small sample size in the Kangaroo Valley. We're looking at the response, recovery and preparation around the black summer bushfires. And we gathered information from all of the residents about what sort of measures they took to prepare their properties for bushfire. And they're ranked here, and bushfire sprinklers rank quite highly. So in that particular sample, which was small, and it's not necessarily representative because they were quite an engaged community, it was about 50% of the households we looked at had some form of bushfire sprinkler system. So they are being used quite a lot. So in Australia, we have we don't have a lot of guidance and research, but compared to other countries, we've done quite a lot, relatively speaking. So back in the year 2000, there was an FPAA report that looked predominantly at the types of systems that were being used at the time. Then there was a CSIRO report put out under the Bushfire CRC in 2010, I think. And it was more of an engineering assessment of these types of systems and made some drew conclusions from research that was existing at the time about what should be looked at and considered when designing a system. I did my PhD on bushfire sprinklers, which was published in 2019, which was aiming to build on those. I was looking at quite a specific area of them. I was looking at the effects of wind on the droplets when they're airborne and how much water gets evaporated or blown away. And then in terms of the guidance that's available to homeowners, we have the Australian Standard 5414, which is probably the most detailed guidance document for sprinkler system design or bushfire sprinkler system design around the world that we've come across anyway. You can also draw knowledge from other areas that are related. So we have standards for traditional fire sprinklers, like drencher systems or war-wetting sprinklers, as they're called now, which can be drawn on and help to inform bushfire sprinkler design. And there's a lot of online published guidance by different organisations. So this is an example from the CSIRO's online bushfire guide, which is quite a good example. They give quite a lot of detail about what can be done to design a bushfire sprinkler system. And the guidance that's available from different agencies on sprinklers really varies in the level of detail and what it's recommending currently. So if we look at 5414, there are some challenges in applying it. This is based on feedback we've had from interviews with the community. So a lot of people have trouble, well, to begin with, no systems appear to have been tested to Appendix A, which to comply with the standard, the sprinkler arrangement and type of sprinkler needs to have been tested using fans and to test where the water ends up when it's sprayed. So without any systems, from as far as we can tell, having been tested, no one can comply with the standard currently, although I'd be very keen to talk to anyone who has tested systems. It currently only addresses BAL 19, so if you're in a different BAL level, it's difficult to understand how to apply that guidance to your circumstances. And it also only applies to, it specifies a system that gives you complete protection, or is designed to protect for BAL 19. So it doesn't differentiate between very vulnerable building materials and building materials that are less vulnerable. And so for that reason, it ends up requiring a really high flow rates of water, which require then a lot of water to be stored in your tanks. So that graph is just showing for an archetypal house of typical sort of dimensions. To protect the whole building, there's the blue line, to protect every surface. And then to protect the just two facades, and assuming that the glazing is all screened, is the orange dashed line. So you're looking at between 20 and 100,000 kilolitres for just the minimum 30-minute duration of operation that the standard requires. But then if you want to operate the system longer, for example, if you want to evacuate early, leave early, operate the system before you leave, you might need several hours of operation, in which case you're looking at hundreds of thousands of litres. So when we consider the science or the physics that's involved and the considerations in designing a system, we break them down in this way. So we look at the water supply system, and here the different sort of considerations are listed with a kind of traffic light coloration. So green is showing there's quite good evidence supporting design decisions. Orange is sort of, there's some evidence but probably more needed. And then red is showing there's not much guidance available currently. So for water supply systems, the pipework design, water tank selection, selection of pipes and protection of pumps and generators, there's all quite good guidance available and knowledge. For automatic or remote activation technologies, which can be important, there's good technologies available, but not much guidance on how to apply them effectively to a bushfire sprinkler system. Then moving on to the spray dispersion, so that's looking at once the water's released from the nozzles, it sprays out into the air, where does it end up? So there you've got to think of things like wind drift, evaporation and splashing and other post-impact transport of droplets. And that's what my PhD was focused on, and there's some evidence there now, but probably more needed. And then system influence, so that's where we look at how does the water actually protect the building? And surprisingly, there's still quite a lot of conflicting claims made about this from manufacturers and designers of systems. So there's a number of different mechanisms listed there that it could be affording protection to the building through, and I'll go through those in a bit more detail later. So the next few slides, I'll just focus on the work we've done on wind and its effects on the sprays. So part of my PhD research was looking at characterising sprays produced by different nozzle types that are often used in this type of sprinkler system. So we used a high-speed camera. We took detailed footage, as is shown in that diagram, of all throughout 6 different sprays, measuring hundreds of thousands of droplets, and then developed some software to automatically measure the size of the droplets, their velocities, and do things like what's shown in the top right of the slide, trying to separate where you've got overlapping images of droplets. And that all produced spatial data for those sprays. which is what's shown in the bottom right image. This sort of level of detail of data isn't needed when you're designing a system, probably, but we needed it because we were planning to simulate the sprays operating in wind. So we needed to know sort of how to release droplets, how big they should be, what the flow rates should be in a spatial sense. We also ran some experiments outdoors in real wind, spraying different sprinklers next to this 2.4 metre cube. So there we were trying to produce very well-controlled data with real wind to use for validating computer models. So I won't go through that in much detail, but we looked at those four different configurations on the screen. And then we took that data and we used it to validate computational fluid dynamics simulations, which is what's shown on the far right of the screen. So this is a method where we build the domain, we assign boundary conditions, so that would include the wind characteristics, the velocity profile and turbulence of the wind coming up towards the building, as well as the droplet release locations, flow rates and droplet sizes and velocities. And then we can simulate where those droplets should end up based on the flow of air around obstacles like buildings. And that's what's shown on the right, looking at the four configurations. And this type of simulation is notorious for being quite unreliable if it's not properly validated. So the results can look realistic, but may not be. And so we undertook this validation, which is shown on the left, comparing the experimental results on the horizontal axis to the simulated water deposition fluxes on the vertical axis. So that's the deposition rate of water on certain areas on the cube. And so you can see there's still quite a lot of discrepancy between the two, up to 50% in some cases, in some locations, but the general trend is captured. So the magnitude of water deposition rates in locations is captured fairly well, and the differences in that deposition rate between different locations on the cube is captured fairly well. So I guess that's the context that you need to keep in mind when you interpret the CFD results. It's not an exact simulation. We then used the validated model to look at 9 different systems. So I won't go through these in detail, but there are some with the sprinklers on the ridge of the roof, some with them near the gutters, and some of them with the sprinklers under the eaves spraying at the building or outwards. The domain in the top right-hand corners, the simulation domain that we used, so we had like an archetypal simple house model, and we looked at different wind directions relative to the house and 3 different levels of severity of wind and conditions, which are shown in the graph in the table. So temperatures from 35 up to 47 degrees, very dry conditions becoming more dry, and different wind speeds up to quite strong wind speeds, 18.5 meters per second. And then this is the kind of result that those simulations produce. So this is for one of those systems, showing the breakdown of the ultimate endpoint of all of those droplets that we're tracking in the simulation, showing, so for example, in the yellow, with the different wind directions, how much of that water is ending up on the walls of the building, on the roof of the building, sorry. And then in the dark red, the walls. So for this sprinkler system, it's showing that about half, depending on the direction of the wind, about half of the water's ending up on the ground, which you'd expect. It's a symmetrical spray near the gutters of the building. But there's quite a lot gets evaporated in some cases, up to about 10% of the water. And then this slide is showing those types of results for all 9 sprinkler systems and for the 3 different severities of conditions. So there's a lot of information there we don't need to digest right now, but basically it's showing that most of the systems aren't too sensitive to the direction of the wind. The systems that spray water directly at the walls from under the eaves, which is the most right-hand column of data, and then the third most right-hand, actually achieve a lot of water delivery to the walls, which is what they're designed to do, without being too severely impacted by wind. But then if you look at the sprinklers on the roof, for example, when the conditions become more severe, there can be sort of 40% of the water doesn't end up on the roof, or more, 50%. More recently, we've also run some tests following Appendix A of 5414. So there's two tests that are specified. You construct a mock-up wall, which is shown there. The diagrams on the left are from the standard. You need to mount the sprays as they're specified to be installed, and collect water using a trough at the base of the wall to measure how much water is actually hitting the wall. And then in the second test, you install a fan to generate a simulated crosswind of 45 kilometers per hour, and you ensure that an individual sprinkler can wet the wall directly below itself. The water isn't all blown downwind from the sprinkler location. So in the photos, you can see our test wall, and in the lower photo, you can see the 6 fans that we used to generate that crosswind. So this is some photos of the test rig operating, and this is some data showing the measured flow rates. We used sort of discrete tubs rather than one trough, so we could get a bit more spatial resolution in the deposition of water. Both of these sprinklers that we test passed the wind test, which is shown by the images on the right, but neither of them delivered water at the flow rates needed to meet AS 5414. But really, these were just example sprinkler systems we were testing the test rig with. We were really more interested in critiquing the method itself. So we looked at the velocity distribution in the region in front of the wall. So these graphs are all showing measured velocities in those 4 different cross sections in front of the wall, showing that even though all of these tests could have been conceivably compliant with the standard, the measured flow rate, airflow flow rate near the exit of the fan, of a single fan, was above the 45 kilometers per hour requirement. Actually, downwind where the sprays are operating, the velocities are much lower. And so we looked at 1 fan operating, 3 fans operating, and 6 fans operating. You could conceivably just run 1 fan and say that you've run the test, but maybe there should be specification made about the uniformity of the flow field or where the velocity needs to be measured. All right, and then moving on from wind drift and evaporation, I've got a few slides just looking at different mechanisms that these sprinkler systems could be protecting buildings by. So the primary mechanism that they operate by is probably the cooling of surfaces, direct cooling by wetting those surfaces. So cooling of glazing and combustible building components. There were quite a few tests undertaken in the US in the late 80s and early 90s of sprinkler protection of glazing, looking more at conventional structural fires, and that's what that image is from on the right. That's showing the test setup. So they found that for tempered glass, sprinklers can be effective at preventing breakage up to about 25 kilowatts per metre squared. But importantly, that's for tempered glass. And they also found that uniform application of the water is really important, because if you wet part of the glass, it can introduce thermal stresses, which can then break the glass. And then the CFD results from our work indicate that for the particular systems that we simulated, sprinklers under the eaves aimed at the walls had enough thermal capacity to remove up to about 50 kilowatts per metre squared for those particular systems. The sprinklers mounted above the gutters were only reducing about 10 or 20% of the incident radiant heat flux, and the sprinklers above the ridge of the roof were not effective at all at cooling the walls, which perhaps isn't a surprise because they're not spraying on the walls. So another mechanism that is sometimes touted as being the mechanism by which these systems work is the attenuation of radiant heat by airborne droplets. And so the graph on the left is showing the spectrum of radiant energy that could be typical of a bushfire scenario with a total heat flux of 40 kilowatts per metre squared. And it's showing, so that's shown in red, and then the dashed and dotted lines are showing if you've got a uniform curtain of airborne droplets with the same bulk density of 100 millilitres per metre squared, how much of that radiant heat is reflected back at the fire or absorbed. And so you can see it depends strongly on the droplet size. Really small droplets are much more effective at attenuating radiant heat. But obviously in a bushfire scenario, the challenge is that those smaller droplets are also affected by wind a lot more. So the question is, can you design a bushfire sprinkler system to maintain that protective curtain of very small droplets in the bushfire conditions? And the graphs on the right are from our CFD, and they're showing that probably a significant protection can't be afforded by this method, at least for the 9 systems we looked at. So some of the systems would operate attenuating almost no radiant heat, but some were attenuating about 20% of the incident radiant heat. So it's a much smaller level of protection than spraying the water directly at the walls. And then very quickly, because I'm eating into the question time, we've also looked very briefly at the potential that airborne droplets might intercept airborne embers. So we had a very simple analytical model. We didn't look at any effects like turbulence. It's just 2 streams of particles passing through each other and looking at how many intersect with each other. And the graphs on the right show those results. And overall, it showed that, again, very small droplets were much more effective, but you have the issues with wind. And if you use larger droplets, they could be effective, but you'd need very large flow rates. And then there are other potential mechanisms which have been claimed, which still need to be looked at in more detail. So extinguishing piles of accumulated embers and debris near walls is obviously a mechanism that could be effective, but hasn't really been quantified in the bushfire context. Wetting fuels in the bush near the building could also be effective at reducing the severity of the impact on the building. But again, we haven't found any evidence that really quantifies that effect. And bushfire protection afforded by indoor sprinklers is another thing that's been claimed, but we haven't seen any sort of quantified analysis of how much protection that is and whether it's more effective to have indoor sprinklers or outdoor sprinklers. So I might skip this because it's I'm eating into most of the question time, but we're looking to, there's room for improvement in AS 5414. There is still a need for more scientific evidence-based guidance, strengthening tools like CFD and through experiments like what's shown here. It's from the IBHS wind tunnel in the US where they're starting to look at this kind of thing. And there's room for innovation in sprinkler systems too. So thanks. Are there any questions?
Yeah, thanks for the presentation. It was really fascinating to see that there's actually a lot of work going into this sort of thing. One of my questions would have to be, with the sprinkler heads themselves, are you guys putting a lot of research? We're still going? There we go. Is there much research going into the different types of sprinkler heads and maybe focusing more on directional sprinkler heads to reduce water wastage in the process and then increase the overall efficiency of the systems?
I'm not aware of bushfire-specific research on developing different nozzles, but there could be commercial research going on. There are some sprinkler products available, nozzles that are sort of promoted as being designed for sprinklers, for bushfires, but I haven't seen any supporting evidence to show why they're more effective than other sprinklers.
It seems quite exciting to see the crossover, even combination of external sprays and the use of internal sprinkler heads. And I guess there's an interesting crossover point around, well, would you actually think about putting sprinkler heads in things like roof cavities and subfloor spaces and whatnot? Have you looked into or thought about that as a logical part of the idea of combining or having a much greater coverage or holistic system?
It's definitely something we've thought about, but haven't done any scientific work on it. I know the Home Fire Sprinkler Coalition is very keen to look at those sorts of hybrid systems for indoor fire protection and bushfire protection. But no, we haven't done any work looking at that in particular.
With your, I guess, seeing, I've read one of your papers, the paper you did about this as well, and seeing your presentation, I guess with the standard for sprinklers, so water storage of, it was like 22,000 litres. I think you mentioned in there that, you know, obviously the more water, the better result you're seeing to get. Do you think that what's set in the standard, the 22,000 litres, is sufficient, or do you think that should be larger?
It's hard to say how long the piece of string should be, I guess. Yeah, because you wouldn't want to limit. So in a lot of circumstances, people might have a limitation on the amount of water they can store, and so they might want design guidance that shows them how to most effectively use the water they can store. And on the other hand, you don't want to give people false sense of security by saying you can just use that amount of water when it's not actually enough. So it's a bit of a balancing act, I think, and I don't have a clear answer.
Sorry if this is a dumb question, but which sprinkler worked most effective out of the ones you looked at?
So it depends on what the aims of the design were. So we looked at those different mechanisms of protection differently. So some of the systems, for example, were spraying the roof, so they didn't protect the walls at all. And one of the systems was spraying sort of away from the building, so it didn't wet the walls at all. But in terms of providing cooling to the walls, it was the system that had flat fan sprinklers, which are like a 180-degree fan mounted under the eave, spraying directly at the top of the wall and letting that water run down the wall.
Was there any research done into using the old market garden sprinkler, but on a vertical plane? I know Bushfire Pro, that's how they've designed their system, so it gives can give a roof and wall protection type deal as well. Was any research of that done?
We didn't look at any of those sort of rotating arms. We did look at this. There was a paper published in the US where they had hollow cone sprinklers mounted under the gutters, spraying out away from the building. And the idea was that the wind that's bringing embers in would bring that water into the same positions that it takes the embers. So we tested that, and it didn't seem to help. It performed relatively poorly compared to some of the others.
There's a question on the app.
It says, is there a favourite type of system that stands out for you in terms of cost benefit to protect existing buildings which have little or no bushfire resistance? So I wouldn't want to recommend a sprinkler system be used instead of other measures without knowing the specifics of the house. I think the same principles that we're looking at for all of the systems would apply to those types of buildings and other buildings. So I wouldn't recommend a specific system, but the data was showing which systems were relatively better performing than others. Thanks.